Imagine paying like over £1,200 for a piece of software, making a single typo in a customer's address and realizing the only way to fix it is to hit the backspace key 50 times.
Oh, no.
Destroying all your own work in the process.
Right.
And then, having to retype the entire paragraph purely from memory. Well, welcome to December 1984.
It is pretty much the absolute definition of technological friction.
Yeah.
I mean, we look back at the dawn of the microcomputing era and we tend to romanticize it.
Oh, absolutely. We think of it as this like rapid, enlightened sprint toward the digital age.
Exactly. But the actual reality of moving a small business from a physical, metal filing cabinet to a glowing green monitor, it was this brutal grinding process of endurance.
Yeah, and that brings us to our mission for this deep dive. We are going to drag you back to that exact moment in time to examine the staggering friction of early digital data management.
We really need to strip away the nostalgia here.
Yes, exactly. We want to look at the raw mechanics, the massive financial costs, the just baffling software constraints, and the hardware realities that completely define computing long before things like cloud syncing or, relational web apps even existed.
And to do that, we have a really fantastic primary source today.
We do. We are relying on a deep dive review published in the December 1984 issue of Personal Computer World magazine.
Right, which was written by a reviewer named Kathy Lang. And she was analyzing a new relational database management system. It was called Files and Folders.
Such an exciting name.
Right, very flashy. It was developed by a software company called ACT Pulsar, and Lang specifically tested it on a highly relevant machine for the British market at the time, which was the Apricot PC.
And we've also run some historical economic data to translate the 1984 pricing into 2026 figures for you.
Because the economic weight of this software is just, it's crucial to understanding why anyone would endure the sheer pain of using it.
Okay, let's unpack this. We'll get to the actual mechanics of the pain in a moment, but let's start with that economic reality because, if you are going to subject yourself to the backspace nightmare I just described, there has to be a compelling reason.
Right, a huge incentive.
The base price for files and folders in 1984 was £295.
Which doesn't sound terrible until you do the math.
Exactly. Factoring in an accumulated 300% inflation from 1984 to 2024, plus the target inflation leading up to our current year of 2026, we are looking at a multiplier of roughly 4.2.
Okay.
So that £295 price tag equates to approximately £1,240 today.
That is just wild. You are dropping the equivalent of like a used car on a thick printed manual, a cardboard box, and a couple of really fragile magnetic floppy disks.
Yeah, it's an entirely invisible product.
And the psychology of that purchase for a small business owner back then is really fascinating. They were buying microscopic magnetic arrangements on plastic, basically just hoping it would somehow save their livelihood.
But I have to challenge the logic of that investment. If this software was as brutally inefficient as our source material suggests,
Oh, it was.
and it cost the modern equivalent of over £1,200, why wouldn't a small business owner just, hire a teenager part-time to manage the physical filing cabinets?
Well,
Was the return on investment actually there in 1984, or was this just early technological FOMO, like businesses wanting to look cutting edge without actually understanding the underlying labor costs?
that's a fair question, but it really wasn't just FOMO. It was an escalating crisis of physical space and access time.
Okay.
Think about it. Hiring a clerk to file paper works fine when you have 100 customers. But what happens when you have 2,000?
Right. You need a warehouse.
Exactly. The physical footprint of fireproof metal cabinets taking up expensive commercial real estate becomes a massive liability. But even more critically, paper is inherently siloed.
What do you mean by siloed?
So if a clerk needs to find all customers who bought a specific part in, let's say, November, they have to physically cross-reference the customer Rolodex, then the inventory ledger, and then the carbon copy invoice stacks.
Oh, wow.
That takes days.
Yeah.
So the promise of the microcomputer, even a really slow one, was that you could index that data. Even if it was painful to input, retrieval was a mathematical certainty rather than a physical scavenger hunt.
Okay, that makes sense. Which means the burden shifts entirely from the retrieval of data to the input of data, and the source material explicitly notes that files and folders was targeted at novices, people completely brand new to computers.
Right.
So you are asking an office manager who has mastered the tactile, forgiving world of paper and typewriters to sit in front of a command line operating system.
Like MS-DOS or PC does.
Exactly, where the default interface is literally just a blinking cursor demanding arcane syntax.
It was terrifying for them. So to bridge that terrifying gap, ACT Pulsar marketed files and folders as a quote-unquote menu-driven experience.
Ah, okay.
And they featured what they called a paint-to-screen format.
Paint to screen.
Right. The concept was revolutionary on paper. Instead of writing procedural code to define database tables, the user would visually draw the data entry forms directly on the screen.
I mean, that sounds like building a basic web form today, like on Squarespace or something, which implies a level of fluidity.
It does imply that, yeah.
But the mechanical execution of paint to screen is where the hardware limitations of 1984 just violently collide with the marketing promises.
Oh, it's so bad.
Let's look at how a user actually designed a database. You type a label, let's say first name.
Okay.
Then you use the cursor keys to draw a line indicating the maximum length of that field. So far, relatively intuitive.
Yeah.
But then you hit the return key.
And this is where it all falls apart. Because the expectation for a modern user is that hitting enter or return confirms the action and frees the cursor to move anywhere, right?
Right. You click wherever you want.
But this software operated on strict linear terminal logic. Hitting return inherently mimicked the carriage return of a mechanical typewriter.
Oh, no.
Yeah, it snapped the cursor to the left margin of the very next line, directly beneath your previous entry. The software's architectural assumption was that all databases were just a single vertical column of fields.
But what if you were trying to optimize your screen real estate? I mean, a standard monitor back then was often, 80 columns by 25 lines?
Exact.
You don't want first name, middle initial, and last name taking up 3 vertical lines when they easily fit horizontally on one.
And this is where the friction of the interface design becomes almost punitive. You didn't have a mouse to interrupt the cursor position and just click somewhere else.
No mice yet.
Right. And you couldn't use the return key, or it would just drop you straight down a line.
So how did you move over?
To place a second field on the same horizontal axis, the operator was forced to press and hold the right arrow key, manually navigating character by character, blank space by blank space, across the screen matrix until they finally reach the desired column.
That is... I mean, it fundamentally changes how you perceive the machine. The screen isn't a canvas at all.
Yeah.
It's a rigid grid, and you are being forced to physically step through every single empty coordinate.
Exactly.
But, the rigidity of the layout is really nothing compared to the reality of actually entering data into the system. Let's revisit that backspace nightmare I mentioned at the top of the show.
Yeah, let's get into that, because Kathy Lang's review points out that records were edited on screen under what the manual proudly called full cursor control.
Right, full cursor control.
But the reality of that control was severely limited by the memory architecture of the program. Within a defined field, there were 0 editing commands available, save for one.
The backspace key.
The backspace key.
Let's really break down the mechanics of why that is so devastating for anyone listening who codes or just types today. Because today, text editors load your string of characters into a dynamic buffer.
Right.
If you click into the middle of a word and type a letter, the software instantly shifts all the subsequent characters forward in memory to accommodate the insertion. It happens completely seamlessly.
But in files and folders, there was no dynamic string buffering for editing. The software treated the field as a fixed array.
Oh, boy.
So backspace didn't just move the cursor backward, it destructively wiped the preceding character from the array entirely.
Which just creates this intense cognitive load on the person typing. I mean, think about it. If you are entering a complex 50-character street address and you miss a single letter in the second word, you cannot just navigate back with the arrow keys.
Nope.
The penalty for noticing a typo at the end of a line is the mandatory destruction of 40 perfectly good characters. You literally have to physically annihilate your own work and retype the entire string from memory. So the user stops focusing on the data itself, right? They start hyper-focusing on the raw mechanics of their finger placement because the software offers 0 forgiveness.
It illustrates the immense gap between how a human brain processes information and how early software engineered memory allocation. I mean, the developers weren't actively trying to torture the user.
It feels like they were.
I know, but implementing dynamic text insertion in 1984 on an Intel 8086 processor within the limited RAM constraints of an Apricot PC, it required complex memory management.
Okay, explain that a bit more.
Well, every time you insert a character dynamically, you have to recalculate the memory address of every subsequent character in that string.
Right.
ACT Pulsar likely just deemed that overhead too computationally expensive for a simple data entry field, so they opted for destructive backspacing. It was mathematically efficient for the CPU and just completely psychologically exhausting for the human.
And the software made even further sweeping assumptions just to save on computational overhead. Lang notes that the system assumed all fields were text fields by default.
Oh yeah, this is a big one.
If you wanted a field for numerical currency, say, the price of an inventory item, you had to explicitly navigate a separate menu hierarchy just to declare it a numeric field.
And if you forgot,
If you forgot, the system treated your numbers as a string of text characters, rendering it completely immune to any mathematical calculation.
it's so unforgiving. But, we really do need to look past the hostile interface, though, because once the data was finally committed to memory, we hit the underlying engine of files and folders.
Yes.
And this is where we actually see a genuine foundational triumph of early desktop computing. Because despite the primitive front end, this was not a flat file list manager. It was a relational database.
We should clearly distinguish the architectural difference there because the leap from flat file to relational is arguably like the most important data concept of the 20th century.
Absolutely.
So a flat file system is essentially just a massive single spreadsheet. If you run a wholesale business and a customer named Sarah buys 50 different items over a year, a flat file requires you to type Sarah's full name, her address, and her phone number onto 50 separate rows alongside each item she bought.
Which creates massive data redundancy. I mean, if Sarah moves to a new city, you have to find all 50 of her historical rows and update the address on every single one.
That sounds like a nightmare.
It is a maintenance nightmare. But a relational database solves this by using pointer mechanisms.
Okay.
You have one file dedicated exclusively to customers. Sarah gets a unique ID number, say 001.
Right.
Then you have a second file dedicated to orders. When Sarah buys something, the order file doesn't record her address. It simply records the pointer 001.
And then the software dynamically stitches the two tables together in active memory when you query it.
Precisely.
Lang points out that files and folders could keep 3 files open simultaneously in RAM and could map up to 8 linked files in a single relational group.
Which is huge.
It really is. Mapping 8 linked tables on a 1984 microcomputer, utilizing pointer logic. I mean, that is the exact same architectural foundation that powers modern enterprise software and the entire architecture of the modern web today.
It is a remarkable engineering feat for the hardware of that era. But, naturally the execution was layered with just baffling constraints.
Of course it was.
To make those relational links function, the software relies on what they call sort keys, the specific fields indexed by the software, to rapidly search and link data without reading the entire disk sequentially.
Okay.
The manual explicitly warned users against defining long sort keys because they would consume massive amounts of processing power.
Right, but here's the kicker. If a user failed to manually define their keys, the software's default behavior was to automatically turn the first 5 characters of every single field in the database into a sort key.
It's so counterintuitive.
It is. The documentation literally warns you that excessive indexing will cripple the machine, and then the software immediately attempts to cripple the machine unless you actively intervene.
It reveals this really profound disconnect between the engineers writing the core data engine and the designers building the user experience logic on top of it.
Definitely.
But I think the real insight into the software's architecture comes from Kathy Lang testing the physical limits of those keys.
Oh, this is my favorite part. Here's where it gets really interesting. The official documentation from ACT Pulsar stated that the absolute maximum length for a sort key was 29 characters.
Okay.
But Lang decided to push the boundary. She essentially just hacked the undocumented boundaries to see when it would break. She created a key that was 46 characters long.
And what happened?
The software accepted it.
Wow.
It didn't crash, it just functioned perfectly. She dryly notes in her review that the actual limit remains unknown.
I mean, how does a software company not know the mathematical boundaries of their own compiled code?
It comes down to how memory allocation worked in early operating systems and, honestly, the somewhat chaotic nature of 1980s quality assurance.
If the manual claims 29 characters, that specific number isn't arbitrary. It likely relates to how the developers divided memory blocks.
Okay, break that down for me.
So perhaps they allocated a 32-byte chunk of RAM for each key, reserving 3 bytes for system overhead and pointers, which leaves exactly 29 bytes for the actual text string.
So if the limit was hard-coded at 32 bytes total, how did Lang successfully enter 46 characters without the system throwing a fatal error?
Buffer overflow.
Ah.
This is a classic hallmark of early software development. The program likely just lacked boundary checking. When Lang typed 46 characters, the software filled the 29 allocated bytes and then simply kept writing the remaining 17 characters blindly into the adjacent memory addresses.
Wait, really? It just overwrote whatever happened to be living next door in the computer's RAM?
Precisely. If that adjacent memory space happened to be empty or held non-critical data, the program would appear to function perfectly normally.
Wow.
Lang just got lucky. If she had overwritten a memory address actively being used by the MS-DOS kernel, the entire machine would have locked up instantly.
That is terrifying.
It is. The fact that the manual stated a limit, but the software lacked the boundary logic to enforce it, proves that ACT Pulsar likely never stress-tested the upper limits of their own variables before shipping the master disks to the duplicator.
It was literally the Wild West. You're paying over $1,000 for software that might silently corrupt its own memory space if you type a name that is too long.
Exactly.
Which brings us to the operational reality of running this engine. Once your data is entered and your tables are linked, how does the software actually handle the daily velocity of business data? Let's look at the benchmarks and the glaring absence of a core feature: batch processing.
Yeah, the lack of batch processing in files and folders is perhaps its most fatal flaw for a serious business environment.
Effing.
Batch processing is the ability to apply a single command to a massive data set simultaneously.
To put that in context for you listening,
Mhm.
inflation in the UK in the early 80s was highly volatile. Let's say a hardware supplier increases the cost of their entire catalog by 10%. With a batch process, an operator writes a single logical query. Locate all records in the inventory table linked to supplier A and multiply the price field by 1.10. The CPU executes the math, and thousands of records are updated in milliseconds.
But without batch processing, that bulk command is completely impossible.
Right.
If the supplier changes 1,000 prices, a human operator has to query the database for the first item, load the record into the fixed array, mentally calculate the new price, use the backspace key to delete the old price, type the new price, save the record to the disk, and then manually request the second item.
Oh my God.
1,000 consecutive times.
It reduces the microcomputer to nothing more than an electronic typewriter with a very good filing cabinet attached. It isn't actually computing the data for you.
Oh, it's not.
Lang even points out that while you could create temporary fields to perform math between 2 points within a single record, the software lacked date and time logic, and you couldn't use it as a simple desk calculator. If you needed to do a quick sum before entering data, you had to physically take your hands off the keyboard and use a desktop calculator sitting next to the computer.
The benchmarks Lang recorded for basic structural management further illustrate the physical drag of the hardware too. She tested a data set of 1,000 records. Now, 1,000 records is trivial today.
Oh yeah, an average smartphone could parse 1,000,000 rows in a fraction of a second.
Exactly. But in 1984, running on an Apricot PC, importing a raw file of 1,000 records took 16 minutes and 10 seconds.
16 minutes just to import.
Just to import.
And sorting those 1,000 records on a simple 5-character field took 14 minutes and 20 seconds.
And here's the absolute peak of the friction. If the business decided they wanted to add a brand new empty field to the database structure, say they wanted to start tracking a customer's postal code,
Okay.
updating the structure of those 1,000 records to include a blank postal code box took a staggering 22 minutes and 4 seconds.
We have to unpack the physical mechanics of why it took 22 minutes to append a blank field. Because this isn't just the CPU thinking slowly, this is a severe limitation of mechanical storage and RAM constraints.
Right. An Apricot PC might have had, 256 kilobytes of RAM? You physically cannot load an entire database of 1,000 complex records into active memory at once.
So the computer has to constantly swap data back and forth with the floppy disk drive.
Exactly. And the floppy disk drive relies on a mechanical stepper motor that moves a physical read-write head back and forth across concentric magnetic tracks on the spinning plastic disk.
It's all physical movement.
Yes. To append a new field to 1,000 records, the software has to instruct the drive head to physically seek the first sector, read a small chunk of records into the limited RAM, append the new structural bytes in memory, instruct the drive head to seek an empty sector on the disk, write the expanded records back to the platter, and then update the master index pointer table.
Wow. It is engaging in thousands of microscopic mechanical movements, The 22 minutes is largely just the physical transit time of the drive head seeking a cross track.
And during those 22 minutes, the computer is completely inaccessible.
Imagine making a pot of coffee, drinking it, and watching your mug, all in the time it takes your computer just to alphabetize a single list of 1,000 names.
It literally dictates the entire rhythm of the physical office. You didn't run a database update on a whim.
Oh,
You batched your physical paperwork all day, initiated the import or the index rebuild at 5:00 p.m., and left the office, basically praying that a slight fluctuation in the municipal power grid overnight wouldn't cause the write head to crash and corrupt the entire magnetic table.
it is a phenomenal bottleneck. And it forces us to ask, was files and folders uniquely terrible, or was this just the baseline reality of the 1984 software market?
Well, Lang's review doesn't operate in a vacuum. She provides a really good comparative breakdown of the industry landscape at the time.
Because if it took 22 minutes to add a field, were the competitors any better?
The 1984 database market was deeply fragmented. It was essentially a battleground of competing architectural philosophies. The dominant heavyweight of the era was DBase 2.
Oh, even people outside of retro computing have heard of DBase. It was the absolute standard.
Yes.
But looking at Lang's chart, it costs £438. Applying our multiplier, that's roughly £1,840 today, nearly $2,000.
But DBase 2 provided the critical functionality files and folders lacked. It possessed a robust programming language.
Okay.
It wasn't menu-driven, it was entirely command line. The learning curve was vertical, requiring genuine programming skills, but it allowed power users to write automated batch scripts.
Ah, so it solved the batch problem.
Yes, it handled flexible key construction and rapid retrieval. It was the tool for professionals who really understood how to manipulate data structures directly.
On the completely opposite end of the spectrum, Lang highlights a program brilliantly named Friday, with an exclamation point. It cost £195, about £820 today, but Friday wasn't relational.
No.
It was a simple single-file flat list system with clumsy screen formatting, though it was praised for having exceptional tutorial manuals for absolute beginners.
Then there was DMS Plus, another £195 system from a British developer. It was heavily stripped down, only allowing one file open at a time. And intriguingly, Lang notes that its indexes had to be manually, quote-unquote, reformed when data was altered.
Let's explain what that means mechanically, because it is a vital concept in database management.
Sure.
An index is essentially a separate, highly compressed lookup table. If you search for the name Smith, the software doesn't scan the entire database row by row. It scans the alphabetical index, finds Smith, and uses the attached memory pointer to instantly jump to the exact location of the full record on the disk.
And in a modern database, the background engine dynamically updates that index table every single time a new record is saved. The software just abstracts that process entirely away from the user.
Right. But DMS Plus required the user to manually trigger the index rebuild.
Oh, wow.
If you spent 3 hours entering 50 new customers and you forgot to run the reform index command, those 50 customers were effectively invisible to the software's search function.
Looking at this market, DBase 2 demanding you learn a programming language. Friday. Refusing to link tables, DMS Plus forcing you to manually rebuild your own search tools, and files and folders taking 22 minutes to update a structure, it reveals a complete lack of standardization.
Absolutely none.
There were no established paradigms for how software should interact with a human being. Every company was just inventing their own unique logic from scratch.
And as a consumer, you were placing a massive financial bet on which company's philosophy would ultimately dominate.
Exactly.
And as an aside, the naming conventions of this era are just hilarious. Why did software names back then either sound like the most boring office supplies imaginable, files and folders, DMS Plus, or an invitation to a weekend party like Friday? Or Pearl?
It's so true. It perfectly encapsulates the identity crisis of the personal computer at the time. Was it a drab industrial machine for processing ledgers, or an exciting new digital appliance that would revolutionize your life?
It was both, depending entirely on which software you booted up.
Right.
But to truly understand the friction of this era, we have to look at the intersection of that software and the physical hardware it ran on. Because even if a user mastered the agonizing interface of files and folders, they inevitably slammed into the reality of hardware clashes.
This brings us to the Apricot keyboard mapping disaster,
Oh, this is the best part.
which is perhaps the most illuminating technical anecdote in Lang's entire review. Files and folders, as we established, was entirely menu-driven, heavily relying on the function keys at the top of the keyboard to navigate through its rigid architecture.
Right.
The software's manual was explicit. The last function key on the screen was always designated as the exit key to back out of a menu.
Which, from a software design perspective, that is a logical standard. Put the exit command at the end of the array.
Makes perfect sense.
However, the hardware engineers who designed the British Apricot microcomputer had a completely different philosophy. They hard-coded the physical keyboard controller so that function key 1 was permanently assigned as finish or exit at the system BIOS level.
So the application software expects exit to be the last key, say F7, but the computer's underlying hardware forces exit to be F1.
Yes. Because of this irreconcilable clash, the software developers had to shift all of their manual references exactly one number out of sync, specifically for the Apricot version.
Meaning, if a user opened the thick 1,200-pound manual to a tutorial on setting up a page format, the printed text might instruct them to press the sequence 14335.
Okay.
But due to the hardware displacement, the user actually had to press 24335 on the physical keyboard.
Every single tutorial sequence in the documentation was wrong by exactly one digit.
It's absurd.
Imagine the absolute despair of a novice user. They are following the instructions perfectly, pressing the keys the manual dictates, and the program is constantly executing the wrong command or violently exiting the module, all because the software developer and the hardware manufacturer had contradictory philosophies on key mapping.
This specific failure perfectly illustrates the world before hardware abstraction layers existed.
What's a hardware abstraction layer?
So today, modern operating systems utilize a HAL, a hardware abstraction layer. The operating system talks to the physical metal of the keyboard, translates those electronic signals into a universal digital language, and passes that standardized input to the application.
Okay, got it.
The app doesn't need to know what kind of keyboard you have. But in early MS-DOS environments, applications frequently bypass the operating system to talk directly to the BIOS interrupts to save processing time. If the hardware varied even slightly from the IBM standard, the software logic completely fractured.
The software was rigidly uncompromising, and that rigidity extended deeply into its security protocols, too. The system managed user access via a numerical hierarchy, assigning users access levels from 0 to 255.
Right. Level 0 allowed basic viewing, while 255 was the ultimate administrative clearance, granting the ability to alter file structures and permanently delete massive datasets.
A numbered hierarchy seems functional, but Lang highlights a severe granularity flaw. Let's say the office manager wants a junior clerk to print a newly formatted report, a harmless routine task.
Sure.
However, because generating a custom layout technically involved creating a new layout file on the disk, the software's file locking logic required the user to possess the ultimate 255 access level.
There was no true read-only function that allowed users to just add records or print without altering structures.
Right. There was no role-based access control. To let someone do something as mundane as change the margins on a printout, you had to hand them the nuclear launch codes. You had to grant them the administrative power to accidentally delete the entire relational database structure just so they could hit print.
It demonstrates that early developers were focused purely on the file system mechanics, like can a file be written to the disk or not, rather than the practical workflow of a busy office where tasks are actually delegated.
But the absolute peak of this rigid architecture, what Lang describes as the ultimate prison for an experienced user, was the ACT loop.
The inescapable menu tree.
Yes. Because the software was designed purely to coddle novices, there were absolutely no command line shortcuts available.
None.
If an experienced operator booted the system and knew exactly which submodule they needed to access, they couldn't just type a path command to jump there instantly. They were forced to physically navigate down every branch of the menu tree, screen by screen.
And returning to the root menu was even more punitive. To exit a submodule, you had to hit the ACT key to back out of each level sequentially.
And remember, that might be F1 on the Apricot.
Right. Lang notes that in some deeper relational setups, an operator would have to press the ACT key up to 7 consecutive times just to claw their way back to the main menu.
It's like being locked in an escape room where you already know all the answers, but the rules dictate you still have to physically solve every single puzzle sequentially just to get out the front door.
Exactly.
By building an environment so heavily structured to prevent novices from getting lost, they created a deeply frustrating cage for anyone who actually learned how to use it.
Which brings us to the ultimate synthesis of this deep dive. When we look at the reality of files and folders in December of 1984, the 1,200-pound cost, the destructive backspace editing, the 22-minute mechanical floppy drive indexing, the manual being one digit out of sync with the hardware.
So what does this all mean?
It forces us to reevaluate our relationship with modern technology. We take relational data completely for granted today.
We really do.
When you type a query into a search engine, or when you buy a pair of shoes on an app, and the inventory system instantly updates a warehouse database 3,000 miles away without a single millisecond of delay, you are relying on the exact same relational pointer logic that was being painfully hammered out in 1984.
The ability to map 8 linked files on a desktop microcomputer was a monumental democratization of data. It pulled the power of the relational database out of the climate-controlled server rooms of mainframes where it was guarded by elite technicians and forced it onto the desks of small business owners.
But the toll it took on the humans bridging that gap was immense. The cognitive load of adapting to software that fundamentally did not understand how human beings think, type, or work.
It was an agonizing but necessary evolutionary epoch. Without the abrasive friction of the 1984 menu-driven interface, the industry wouldn't have possessed the failure data required to design the fluid, predictive user interfaces we rely on today.
Yeah.
Which leaves us with one final, highly provocative thought, derived directly from the source material. A mechanism we haven't discussed yet, but one that fundamentally alters how we view the people who survived this era of software.
Let's delve into it.
Kathy Lang mentions that for all of its relational power, Files and Folders was entirely incapable of printing personalized letters natively.
Okay.
If a business wanted to execute a mail merge, say, sending a customized promotional letter to their 1,000 customers, the database could not do it internally.
So what was the workaround?
The workaround was draconian. The operator had to instruct Files and Folders to export the customer data as a raw, comma-separated text file onto a floppy disk.
Okay.
Then they had to close the database, swap disks, boot up a completely separate word processing program specifically, WordStar, and manually instruct WordStar to ingest the raw text file to execute the print run.
Wow. She also notes that to perform complex mathematics, users had to export their data into a DIF format file data interchange format just so they could feed it into a standalone spreadsheet application like VisiCalc or Lotus 123.
Think about the immense technological burden that places on the operator. Because the software was isolated and constrained, the human being was forced to become the manual API.
The human was the API.
You couldn't just click a share button. You had to intimately understand the internal architecture of a relational database. Then you had to understand the exact syntax of a DI file. And then you had to understand the ingestion protocols of a completely disparate spreadsheet program.
The human had to ferry the data across the void.
Exactly. It is a profound observation. It shifts the human from a passive user to an active, structural component of the data pipeline. Did the violently fragmented, terrible design of 1980s software accidentally invent the concept of the tech-savvy power user?
That is a really compelling thought.
Today, our software is entirely frictionless. Operating systems obscure the file structures. Apps communicate via invisible background APIs. We don't need to know how the machine works to operate it.
Right.
But in 1984, the brutal constraints of the software forced an entire generation of office workers to intimately understand file extensions, memory limits, hardware mapping, and data interchange protocols just to execute a basic mail merge.
Yeah.
Did that abrasive friction inadvertently forge a generation of highly capable digital problem solvers precisely because the machine refused to do the work for them?
It challenges our modern pursuit of seamlessness, doesn't it? When the environment is entirely devoid of friction, the user is never required to conceptualize the underlying mechanics.
Exactly.
When the machine breaks, the modern user is helpless. The 1984 users simply opened the manual, accounted for the hardware offset, and manually rebuilt the index.
It is something to seriously consider the next time you feel a surge of annoyance because an app takes 3 seconds to load. We crave the frictionless experience, but perhaps the struggle against the machine is what actually teaches us how to command it.